Hey guys, Darian Giuseppe here, back again with another video for the Key Concept series. In this video, we are going to look at a past paper question on differential equations. Differential equations shows up in module 3 for Pure Maths Unit 2. And it always shows up. It always shows up right at the end of the exam. So for sure, you could be guaranteed a question like this in your exams. So let's get straight into the question. The question says, or is asking us to solve the differential equation. And this is the differential equation here, right? This is the differential equation that we are given or be asked to solve. So in the exam, we can be asked to solve two types of differential equation: first order differential equation and second order differential equation. The first thing I like to do is identify what type of differential equation this is. Is it first order or is it second order? First order differential equations are differential equations where you have just dy dx in the differential equation. Second order is where you have d2y on dx squared. So based on that knowledge, we can safely say this is a first order differential equation because it just has dy dx, no d2y on dx squared inside the whole dance here or inside that differential equation. So that's cool. That's very important to identify. So we know it's a first order differential equation. How do we solve this now? We can solve this using the integrating factor. However, the first thing we need to do is make sure that it is in a particular form. And that form is dy on dx plus p by y is equal to q, where p is a function of x only and q is a function of x only. Or they could be constants, right? They could be constants too, or constants, right? That's very key. So that's very key. So we want to bring it into this form. We want to bring this guy here into this form. So that's what we want to do first. And then we will introduce the integrating factor and use the integrating factor to solve this first order differential equation. So let's get into bringing this into the form that I spoke about just now. So let's write down the differential equation and just kind of manipulate it a little bit. And this is what we have happening here. So this is the original differential equation that was given by the question. And all we did, right, we look at the differential equation, we see this here is a q and this is a p. All I did was basically, I noticed that we have, this is a function of x here and you have your y. So that's very key. And then this function here is a next function of x only. So we see in that the form has been achieved. Dy dx, there's a dy dx. This would be a p, and this is your y is equal to q. So once you identify what is your p, q, dy dx should have a coefficient of 1. That is key as well. You are good to go here. So this is the form that we are looking to use. Once we have it in this form, we're good. This form is great. So now what we want to do is introduce that guy called the integrating factor because he is going to help us solve this differential equation. So we say integrating factor is equal to, or it's given by e to the integral of p. That is very key. So p, remember, is this 1 on x by x plus 1. So the integrating factor is always given by your if. They always say if is equal to e to the integral of p with respect to dx. So that is key. So that is why we have this here. So that is the general rule. The integrating factor is equal to e to the integral of p here. So now you have to bring forth all your integration skills into play, right? Or all the rules of integration that you know, recognition, integration by substitution, if, right, it is needed here, integration by partial fractions, integration by parts, right? You have to look at this function here and make sure, well, you can integrate it using the rules that you would have learned in module 1. So you see actually the tying in of module 1 into module 3, right? Here. And if you look at this, recognition wouldn't work. But integration by partial fractions will work. You'll notice that if you could express this function here in terms of its partial fractions, it will break down into smaller fractions that can be easily differentiated. Not differentiated, integrated. This is integration we're looking at here. That could be easily integrated, right? So what we could do next is, and I'm not going to go in depth into the partial fractions, but I'm going to just put down the solution for the partial fractions, or for this expressed as its partial fraction. And what you will get is this here. So we get here, so this would be equal to these two fractions here. These two would be the partial fractions. And we get A to be, what is A? A is 1 and B is -1. So what we will do is just put this inside here where your A is 1 and B is -1. So that's what we will need to do in the next. That's the next thing we would need to do. So let's do that here. And this is what we will get. So this is, right? So these two fractions here is basically this, right? That's basically it. So your A was 1, your B was -1. You're seeing that there. So we have these two partial fractions. We can now integrate these two easily. You could see these could be integrated by recognition easily. If you want, guys, you could just pause the video, check this out really quickly, and make sure you understand what is going on there. So let's move forward here. We're here. So let's just integrate this. The integral of 1 on x is ln, and the integral of 1 on x plus 1 is also ln of x plus 1. So I don't know, did I say that correctly? The integral of 1 on x is ln of x, and the integral of this here would be ln of x plus 1. So this is what I'm saying here. This is what we get. And you could actually combine these two using log rules. So this would be actually the ln of x on x plus 1. So this is what we have. And then you should notice that e to the x and ln x are inverses of each other. So they will cancel off with each other and leave you behind with x on x plus 1. And this is it. This is our integrating factor here. So once we have that now, we in the home stretch to getting the solution to this differential equation. The next thing we do is we need to write down the formula for the general solution for this differential equation, right, using this integrating factor here. So that general solution is given by this here. It is given by y by the integrating factor is equal to the integral of the integrating factor by q. You see this little formula here is very, very important. Well, let me write it down. The general thing, right? It is y by the integrating factor is equal to the integral of the integrating factor by q with respect to dx. So y by the integrating factor is equal to the integral of the integrating factor by q with respect to dx. And we know q is this guy here. Remember? So that's why we have this here. So that is basically it. All we need to do now is replace what we found the integrating factor to be here and here. We need to do that. So what we will be doing next is actually taking this guy here, which is the integrating factor, and substituting him here and here. So that is what we do next. And we almost there. We almost at the finish line here. Let's just substitute again here. And something nice will happen here. I hope you guys can see it. Right? Some cancellation. This and this will cancel off nicely. So that looks really good. And what will it leave us with to integrate? That's the question. We get x by e to the negative x squared. Okay, cool. The question is, how do we integrate this? This is the next challenge. And you see, you're going back to your rules of integration again. Recognition. Can we solve this using recognition? Can we solve it using integration by parts? That is the two things that come into mind initially. Integration by parts or recognition. And if you cast back your mind to integration by recognition, we could actually use integration by recognition for this. Parts would work too. I believe parts should work as well, but parts may be lengthy. So I would try to avoid parts for this. It might be lengthy. So I wouldn't use parts, but what I'm seeing is recognition. There's a rule, a recognition rule that says the integral, if you are given, or if you are asked to find the integral of f prime of x by e to the f of x with respect to dx, it is the same as, or the integral of this is equal to e to the f of x. So I'm seeing that we could probably introduce that, or we could employ this rule here, right? What you notice, this is the f of x, but f of x is negative x squared. The derivative of negative x squared is actually negative 2x. It's negative 2x, but this is actually just x in front here. Remember, we need to have the derivative in front here. That's what the rule is saying, but the derivative of f of x, which is negative x squared, is negative 2x, but your f of x is actually x in this case. So this is a question where you have to kind of introduce some constants into the dance, right? And this is what we need to do here. We need to put in a half here, or rather negative a half, and find the integral of negative 2x by e to the negative x squared with respect to dx. This guy here is the same as this. Reason why is because we could bring this half inside here and multiply it by the negative. We could bring the negative a half outside here and multiply it by the negative 2. And that would give us positive 1, which is what we had originally. So that's what we need to do. That is the rule, right? And questions like this always come up where integration by recognition is concerned, and these types of forms, right? Remember, there was a list of different forms where integration by recognition is concerned that we looked at. So this is one of the forms, and they love to bring these forms. And if you know the forms, it helps a lot to get your answer quickly. So, as I said before, let's introduce the half, the negative a half, and the 2 into the dance here. Recall. So now, here we have the setup. This is the f prime of x, and this is the f of x. So simply what we could do now is this. Our integral would be negative a half by e to the negative x squared, right? Remember, that's the rule. So, and we have to remember to plus c, right? Our constant of integration. And we're almost there. We right at the end here. Now we just have to make y the subject of the formula and send this to divide it by this and the c as well. So we can get the final answer here. It will be this here, right? So take a look at it. I know this was a lengthy question, right? The solution, but this always comes up. The last question in the exam, they always bring this type of question, whether it be a first order or second order. The second order questions are actually much longer than the first order. So guys, this is the solution to this question here. Look at it, analyze it, take it in. Feel free to share the video to somebody that you believe it will help. It will be beneficial to. Like the video, just click that like button and subscribe to the channel, and I will see you in the next video.